Okay, so we're going to do 26.7 now. Motion of a dipole in an electric field. So we already know what a dipole is, so we can hopefully understand how this works. So recall that a dipole is two charges. They don't necessarily have to be small. So let's just say two charges separated by a small distance. The distance does have to be small. They are separated by a small distance, d, for example. And then, so we can say that a dipole is shown below. So we have the charge, let's call this Q, positive, and then minus Q, and they are separated by distance d. Okay, so this is a dipole, and this dipole has a dipole moment. I'll write that again. The dipole moment is P, and this dipole moment P is given by the charge times the distance between the two charges. So that's your dipole moment. So if we place this dipole in a uniform electric field, we will expect something to happen. Suppose we place a dipole in a uniform electric field. So we know that we can have a uniform electric field between the plates of a parallel plate capacitor. So we place a dipole like that between in a uniform electric field. The distance between the charges is d. Okay, the electric field is E. So in this electric field, we will expect that there is a force this way. So this is force 1, and then there will be another force that way. This is force 2. Okay, so we can expect that the dipole will be twisted in the electric field so that it lines up with the field. So in the end, this is what we shall have. So this is the field. So the dipole should end up lined up with the field that way. Okay, so the dipole experiences a rotation this way and a rotation that way. So it experiences a torque which will line it up with the field. So we can say that the dipole experiences a torque causing it to rotate so as to line up with the field. Okay, so let's look at how that works. So this is our electric field. We can put the charge here, Q. So we have one force, F1, second force, F2. The positive charge lines up with the field in this direction. The negative charge is that pointing that way. Okay. So this angle can be theta. And so we can say that the net force or the net torque on this charge is equal to the sum of the clockwise torque plus counterclockwise torque. Okay. Note that there is no counterclockwise torque, so that is 0. So the net torque is all clockwise. Okay. And we know that torque is equal to lever arm times force by definition. The torque is the lever arm multiplied by the force. So if you look at it this way, then we can say that let's do a lever arm this way. Let's call this R1, and let's do this lever arm and call it R2. Okay, the distance here, of course, is D, so half of that will be D over 2. So we are saying that there's the lever arm is the distance from the pivot point to the line of action of the force. So we're talking of this distance here, R1, and this angle is theta now. Okay, so the torque, so we can say that the torque 1 is equal to R1 F1, and is equal to R1, which is equal to R sine theta times F1, where R1 is R sine theta. So the R is this distance here. That is also R. R is equal to D over 2. Okay, so our R is D over 2, half of the distance D. In the same way, torque 2 is R2 times F2, which is equal to R sine theta F2, where again R is equal to D over 2. Are you all seeing that? And let me make a correction here. I put that in the wrong place. So what I want is to put it in this direction here. My mistake on that. Hold on a second. Okay, that's R2. So the distance from the pivot point to the line of action of the force is R2. Okay, so everything else stays the same. So the total or the net torque on this is equal to torque 1 plus torque 2, which is equal to d over 2 d over 2 sine theta F1 plus d over 2 sine theta F2. But since the charges are the same, since charges are equal and the distances are also equal, distances are equal, charges are equal, so F1 is equal to F2, and we can say that's just F. Okay, so we can say that the net torque is just going to be d over 2 sine theta F plus d over 2 sine theta F. That will be equal to d sine theta F. And so we can write torque to be just equal to d times F. Let me rewrite that. I don't want it to look like derivative of F. So hold on a second. So this will be F times d sine theta, where we are saying that the force F is equal to the charge Q times the electric field E, according to Coulomb's law. So we can write the torque now as Q times E times d sine theta, which can then be written as QD times E sine theta. And we will note that Q times D is equal to P, which is our dipole moment, the dipole moment that we originally found above. And so the torque can be written as P E sine theta, and by using the cross product notation, this becomes equal to P cross E. Note that these are all vectors, of course. So the torque of a dipole in an electric field is given by the dipole moment crossed with the electric field. Torque is dipole moment crossed with the electric field for a dipole in an electric field. That is the basic formula. So that is the end of chapter 26. So far we've done chapter 25 and 26.